Welcome to the lecture of the course Computational Hydraulics. We are in module 4, surface water hydraulics, and this particular lecture class I will be discussing gradually varied flow in open channels, and this is unit number 1. Learning objective for this particular lecture: at the end of this lecture, students will be able to solve gradually varied flow problem for open channels. We have seen this basic structure of our computational hydraulics course. We have problem definition, mathematical conceptualization, domain discretization, then numerical and discretization algebraic from solution process. In our groundwater hydraulics, we have started from this one dimensional, two dimensional case, and finally derived the hydraulic head distribution for 2D space and 1D time. Now, in surface water hydraulics, first we will start with this channel flow. Channel flow is essentially one dimensional flow due to conceptualization of the problem, and in channel flow, flow depth is one of the important parameter, and flow depth varies with x. So, y, if y is the flow depth in a particular open channel, this is the channel bed and this is the water surface, then flow depth at any particular location y, it is a function of x. Now, we need this variation of y with x for this particular unit. Now, governing equation for gradually varied flow in prismatic channel can be written as dy by dx, and this is S naught minus SF 1 minus Fr square. S naught is bed slope, SF is energy slope, and Fr is the Froude number. Now, to solve this problem, we need initial condition. Initial condition, when I talk about initial condition, we may think this particular condition like 0 time condition. If the flow depth is specified at a particular section in the channel, then we can find out the variation of y with x in the channel. So, this is initial value problem, and this is first order ODE equation. In this case, y is the flow depth or depth of flow, x is coordinate direction, S naught is bed slope, SF is friction slope. Now, SF can be calculated using this expression, and Froude number is can be calculated using this particular expression. Q is the discharge, T is the top width, G is acceleration due to gravity, and R is hydraulic radius, A is cross sectional area. Now, as per our general format that we have discussed in lecture 7, we had discussed the format where d phi by dt equals to psi t and phi. This format was there. Now, in our problem format we can write it as dy by dx, and psi is the general function which is varying with x and y. Now, if we consider this GVF or gradually varied flow condition, then S naught is given parameter, then N is Manning's roughness coefficient, Q is discharge, R is hydraulic radius, R can be calculated as A by P, where P is the weighted perimeter, A is cross sectional area, Q T is the top width. Now, we can express this problem as psi as a function of y only, because there is no x in these expressions. So, we can directly calculate the psi x y using the variation of y only. Now, if we consider a general trapezoidal section, then area we can divide it into two parts. This is flow depth, this is bed width, and left side we have 1:m1, 1:m2 slope. Now, this intermediate area is by, and on both sides if we consider, then this will be the area. Perimeter is this one, bed width or this part, this is the weighted perimeter or P we need to calculate. Then we need top width is this one, and R, obviously R we can calculate based on A and P values. Similarly, if we have circular cross section, we can calculate this area using this formula, where D is the diameter of the section, Y is the depth of flow, theta is this angle, this particular angle, and T is the top width, and P is again weighted perimeter, R is hydraulic radius, T is top width. From our problem definition, we need to find out the nature of the flow. In gradually varied flow, we can classify the flow based on two flow depths. One is critical flow depth, another one is normal flow depth. Now, let us see how to find out this critical flow depth for prismatic channels. Now, in this case, Fr we already know as square root of q squared T by Ga cube, this is equals to 1, because in case of critical flow Fr should be equal to 1, and in rectangular channel, which is the most simplified case, this is B, and for flow depth, if this is Y, then we can calculate the area. Area is nothing but B into Y, and top width is B only, because there is no variation in this sectional parameter over depth. So, if this is 1, then we can find out this is q square. So, T is B, which is top width of the rectangular section G, and A is B y whole cube. So, this is nothing but q square divided by G B square and y cube equals to 1. From there we can get this critical depth expression for rectangular channels. Now, if I want to calculate the normal depth, so normal depth can be calculated from Manning's equation. In Manning's equation, if we write q equals to 1 by n r to the power 2/3 s to the power half or s naught specifically in this case into area, then for normal depth b into y n and b plus 2 I n. So, q is given, b is given, n is given, s naught is given. So, only unknown parameter here is y n. So, this is one nonlinear equation. Now, we need to solve this equation to get the value of y n or normal depth. Now, what we can do, we can form one function which is g y n. G is a function of y n or normal depth of flow, and we can transfer this q on the right hand side and write it like this and equate it to 0. And we already know the Newton-Raphson method. In Newton-Raphson method, let us say we are considering our y n value which is at p g p, and this is equals to let us say g y n p plus del y n. Now, in this case there will be another term, that is the first order derivative term for this case, because we are expanding this term with Taylor series. So, if we expand this term, obviously we will get one term which is g prime and y n, this is with p minus 1, this is p minus 1, ultimately this will become p. So, this is p minus 1 only, and we can multiply this y n. Now, at convergence point this should be 0. So, what we can do, we can write it as y n equals to minus our g y n p minus 1 divided by g prime y n p minus 1. G prime is nothing but derivative of this function g with respect to y n. Now, we can write this one as this equation. So, this is nothing but the expanded form of our derived case, and in case of rectangular channels this g prime can be calculated like this. If we take our nonlinear expression g n, we can differentiate it with respect to, this is g prime y n equals to g yn, and this differentiation is with respect to y. We can get this value. Now, possible flow conditions. So, now we have information regarding yc, yn. Now, according to the position of this critical depth line and normal depth line, we can classify the flow and classify the flow conditions. If normal depth line is above critical depth line, then we can call this condition as a mild slope condition. If a critical depth line is above normal depth line, we can call this condition as steep slope condition, and if normal depth equals to critical depth, in that condition we will call this one as critical slope. If S naught less than 0, then we will call it as adverse slope, and for S naught equals to 0, we will have horizontal bed condition or horizontal flow condition. Now, in this case, we can summarize the thing. For mild slope with the symbol m, yn is greater than yc. Steep slope S, yn less than yc, this is supercritical flow at normal depth. Critical slope yn equals to yc, and horizontal bed slope S naught equals to 0. Adverse slope we have S naught less than 0. From our lecture 7, we can extend the concept of Euler method for solving our this gradually varied flow problem. Now, for gradually varied flow problem, we already know that dy by dx can be represented like x and y. Now, if we write this forward Euler method, then this is explicit in nature, because on the right hand side all terms are known terms. So, yn, xn, yn, these terms are known terms. So, from our problem classification point of view, this is explicit in nature. So, forward Euler, if we open our Scilab code, then we can see that Scilab now we can open this GVF forward Euler. Let us say that for given data q equals to 20 meter cube per second, S naught equals to 0.0008, n equals to 0.015, and bed width is 15 meters. This n is Manning's roughness, g is acceleration due to gravity, Lx the length under consideration, we can consider this length as 200 meters, and y naught, this is the initial depth at x is equal to 0, we can consider it as 0.8. Now, to solve this problem, because we have Q, S naught, N, B, G, these parameters are available for flow in a rectangular channel. Now, if we consider this flow condition with M node, that means nodes in the x direction, that is M node equals to 201 nodes. We have 200 meter length and 200 n nodes are present, and we are considering that these Q, S naught, N, B and G, these are global variables. That means, if we write multiple functions, we can directly utilize the constant values or constant given data for this case. Now, to calculate critical depth, Yc equals to Q square G B square to the power 1 by 3. So, that way I have calculated this Yc or critical depth calculation. Now, for normal depth calculation, we need Gyn and G prime Yn calculation. So, this Gn is this function, this is Gval equals to G fun C y, and this Gval is as per our expression S naught to the power half B to the power 5 by 3 by n, this expression is there. Now, if we consider the derivative of G or G prime, then this is the G prime that we have calculated. Now, after writing these two functions, we need to write the basic structure for Newton-Raphson, so that we can calculate our Yn on normal depth. So, for Newton-Raphson we need that epsilon or error parameter, and absolute error, let us say this is equals to 1, and Yn we are starting from critical depth. Whatever critical depth we have calculated, we will utilize it as initial guess for our problem. Now, with this, if we start this iteration loop, now A error equals to 1, that means absolute of A error is greater than epsilon max, whatever is specified here. Now, this error is G function divided by G prime calculated at Yn, whatever initial value is there, and we are updating this value with Yn equals to Yn minus A error, or Yn equals to Yn minus G by G prime Yn. So, now from this iteration we will get the normal depth for the problem. After getting this critical depth and normal depth, we can identify the possible flow condition in the channel. So, for this problem, if I run up to this step, then we can see that our critical depth is 0.5658 and normal depth is 0.8478. So, obviously, in this case normal depth is greater than our critical depth. So, the flow condition is with mild slope condition or M condition. Now, in this code, next part is our main calculation or dy by dx calculation. In dy by dx calculation, this psi is our function psi x y. We have this A y, which is the area, P y weighted perimeter. So, R is A by P, and SF is calculated like this, which expression is already there in the slides, n square q square r to the power 4 by 3 a to the power a square, and FRS which is Froude number square. So, q square b, again this g a cube is there, because this is q square t by g a cube, which is fr square. Now, from there we can calculate dy by dx. Now, if we call this function, we can utilize it in forward Euler method. Now, forward Euler method, let us generate the grid points or x coordinates. So, xc is line space 0 to Lx, and m node is the number of nodes in x direction, including the endpoints, and delta x is Lx by m node minus 1. So, initialization yb is the y value or flow depth value, zeros m node 1, yv or 1 equals to y naught. Now, in this case, if we run this loop from 1 to m node, so that if we take 1, this will be yv 2 equals to yv 1 plus delta x, and this is psi xc I or xc 1 xc in this case 1 and yv 1, we can calculate the psi value or derivative value, and finally we can get the updated flow depth in downstream section. With this we need to plot the results. So, plotting first is this xc is the x coordinate, yb is the y coordinate or flow depth value. Now, set GCA, this line is written so that we can add another line on top of the present plot. So, we need to add this normal depth line and critical depth line in the plot. So, this is forward Euler method. Now, let us run this problem. So, if we run this problem, we can see this top line, this is actually normal depth line, the bottom line is critical depth line, and our flow condition, this is as per mild slope condition, and this is zone number 2 as per our classification. So, we have M2 profile here in this case. Now, we can utilize other methods. this modified Euler method. In modified Euler method, we have this K2. K2 again, this is calculated from K1. This K1 is similar to our Euler step, but K2 is calculated at half of that or half step. So, let us utilize this one for our problem. Now, if I open the code corresponding to modified Euler, which is the first approach, top portion starting from given data, critical depth calculation, normal depth calculation, these are same as given in our forward Euler method. Only change is there in case of these steps. These are internal steps. Now, we need to calculate this K1 with XC and YVI, and K2 which is calculated at half this del x by 2 and K1 by 2, and we need to add this K2 with YI, so that we can get the final plot. Now, if I run this code again, we are getting plots which is similar to our old one. Obviously, there is some amount of difference in the plot. If we zoom this portion, then we can see that some amount of difference is there between these two solutions from forward Euler method and our modified Euler approach, which is a two-step approach in this case. Now, again if we apply this second approach, this is, which is Euler-Cauchy approach and modified Euler two-step method, and this is average of K1 and K2. In that case, only difference is here this K1 K2 calculation, this is full step for K2 calculation and K1 is full. In previous case we have used half here. Now, in this case we are taking average of K1 and K2. So, if I run this code again, it is coinciding with one of the cases, but this is not the forward Euler method, but the second order approach or modified approach that we have utilized in our previous code. So, some amount of difference is there in this case with the forward Euler method, but not with the first approach of the forward Euler modified Euler method. If we utilize our RK2 again we need to calculate this K1 and K2 as per these expressions. So, in that case only change is there for this K2, K1 is similar to our previous one, but this 2/3 delta x and 2/3 k1 is a different thing, and the final step 1/4 k1 and 3 k2, this is there. So, if we run again this problem with other color, maybe magenta color for this one. So, again it is coinciding with our previous solution. Now, in this case we can see that solutions are converging for our first order and for second order methods to a single solution. Now, in case of our M2 curve, this is decreasing in nature. Now, if we utilize our RK3 method, which is considering K1, K2, K3 with these expressions, now we can utilize it for our problem. This is RK3. Now, in RK3 other portion that is similar, only change is there in terms of K2 and K3 calculation. Now, we can take average or weighted average of this K2, K1, K2, K3 slopes, and we can get the final output. So, if we run this code again, we will get the solution and solution of the same nature. Similarly, if I utilize this RK4, so RK4 also we need 4 terms K1, K2, K3, and in RK4 we need to change the program at this internal step. This is K1, this is K2, K3, K4, and again we can take weighted average value here to get the final flow depth value. Obviously, one thing is clear in this case, that whether we are considering a second order, third order methods, always these methods are explicit in nature. If we consider K1, K1 depends on y n. So, K2 depends on K1. K1 is again known quantity from our previous step. K3 calculation we need this K2. So, K2 is coming from here. If we see this K1 is coming from here to calculate K2, again for K3 calculation we are utilizing K2, again for K4 calculation we are utilizing K3. Now, all these methods whether of forward Euler, modified Euler first approach, modified Euler second approach, RK2, RK3, RK4, these methods are explicit in nature. So, these are the codes that I have written, and I will supply this so that you can run these codes and get the result and verify whatever I have showed during this lecture class. Thank you.